7.5 Scalar and Vector Projections. When two vectors, A and B, are placed tail to tail, such as the following, we have, now note that I have the A is a projection from O to A and vector B is from O to B. And theta is the angle between the vectors A and B, such that there is an angle that is anywhere between 0 and 180 degrees. The scalar projection of A on B is noted as ON. And you'll notice ON in purple. And this means that vector A is projected onto B at a right angle, so that ON is the projection of A onto B. Now, this diagram works if theta is between 0 and 90 degrees, which means that it is an acute angle. What happens if it's obtuse? Well, looking at the next diagram, you see that vector A is a projection onto B where theta is between 90 to 180. That projection is an extension of B, so O to N is an extension of B such that A projects onto B at a right angle. Finally, what happens if theta is equal to 90 degrees? Well, the value of ON there is equal to 0 because it is already at a 90-degree angle. This formula you see in orange represents the scalar projection of ON, and it is a representation of the cos theta. So ON is a scalar projection of A on B such that it equals the magnitude of A times cos theta. Let's go on to the next page. Note the obtuse angle and the right angle. Next page. Calculating the scalar projection of A on B, using the dot product formula, we find that A dot B is equal to the magnitude of A times the magnitude of B cos theta. Somewhere in there, you should see ON. Hopefully you found that the magnitude of A times cos theta is your ON. Note the red brackets. So A dot B is equal to now ON times the magnitude of B. Isolate for ON, and you find out that ON is equal to the magnitude, A dot B divided by the magnitude of B. Now, try and remember the formula. If it's A on B, it's the dot product, A dot B, over the magnitude of B. So think about it as A on B, it's the dot product on top of the B, so on B. Hopefully this is a way to remember the formula. Next part, calculating the scalar projection of B on A. What will that look like? Well, this time we take B and we're projecting it onto A to make a right angle. Well, take the formula A dot B equals the absolute value of A times the absolute value of B cos theta. Isolate for ON. This time it will be B cos theta. All right, and you find out that ON is equal to A dot B on A. Remember how I had you remember the formula. If it's B on A, it'll be the dot product over the magnitude of A. So it looks like that the dot product is on A. Now looking in the textbook, if you look for this on page 391 for further explanation of this, you're more than welcome to look for it and research for yourself. Next part. we have vector projection of A on B. So the last time we had was a scalar, so it's a certain number. Now we're looking at the vector projection. The vector projection of A on B is equal to the scalar projection multiplied by the unit vector. Now, specifically, if you look at it as the scalar projection of A on B, then it's multiplied by the unit vector of B because it's projected onto B. So, the scalar projection of A on B is equal to the dot product over the magnitude of B, and the unit vector in the direction of B is equal to vector B over the magnitude of B. That's the unit vector. Notice the bottoms. Hopefully you notice that the bottoms can be combined to give you the magnitude of B squared. On the top you still have A dot B, and you still have that vector B that belongs to the top. Now, the way to remember it is that it's A dot B over B dot B times B when we're calculating the vector projection of A on B, and note that vector B cannot be the zero vector. In R3, there are three direction angles. There's alpha, beta, and gamma. Alpha is made with the x-axis. Beta is made with the y-axis. And gamma is made with the z-axis. So again, it's the vector with the x-axis is alpha, the vector and the y-axis is beta, and the vector and the z-axis is gamma. The direction cosines for OP is equal to the component vector A, B, and C, such that cosine of alpha is equal to A over the magnitude of OP. Cosine of beta is equal to B over the magnitude of OP. And cosine gamma is equal to C over the magnitude of OP. Now note the numerators. Alpha corresponds to the x value. In this case, in the component vector OP, the value is A. Beta corresponds to the y value. B corresponds to the y value of OP. And gamma corresponds to the z-axis, which the z value is C in the vector OP. So again, the angle that OP makes with the x-axis is alpha, the angle that OP makes with the y-axis is beta, and the angle that OP makes with z-axis is gamma. The vector, example 1, the vector A, negative 2, 5, component vector, is projected onto the x-axis. What is the scalar projection and what is the vector projection? First thing you have to know that the x-axis vector we represent as I. It's the unit vector I, which is represented by the components 1, 0. The scalar projection of A on I is equal to A dot I over the magnitude of I, which is equal to magnitude of A cos theta. We don't need the cos theta this time. All we need is the dot product over the magnitude of I. We find out that that value is negative 2. The vector projection of A on I, again, is the dot product of A dot I divided by I dot I, or magnitude of I squared, times I, the vector I. And that equals negative 2 over 1 times the vector 1, 0. The result will be negative 2, 0 as a component vector. Example number 2. Determine the angle that the vector OP 1, 2, and 4 makes with the y-axis. So, in order to make with the y-axis, we look at the unit vector, j, so that it's 0, 1, 0 in 3 space. Cosine of beta, because again, it's the angle that makes with the y-axis. Cosine of beta is equal to 2 over the magnitude of vector OP, which equals 2 over root 21. And beta equals some value, and you can do that using the cos inverse of 2 over 21, which is 60-something degrees. Example number 3. Find the vector projection of A on B. The key is we need to determine the vector ON. So it's a scalar projection multiplied by the unit vector. So it's A dot B over magnitude of B times B over the magnitude of B. That equals 20. After determining the calculations, we find out that the answer to this question is 32 over 74 for the scalar projection times by the vector, which turns out to be 112 over 37, 64 over 37, and negative 48 over 37. All right, folks, that's everything for this unit. Hopefully this has helped. See you soon.